Last example. The maximum load a horizontal beam can support if held up at both ends is jointly proportional to the width of the beam and the square of its depth, while inversely proportional to its length. Oi, let's see if we can figure out what that means before we try to do this. So first of all, we've got some horizontal beam, right? So that we've got some beam, and it's being supported at both ends, right? It says maximum load a horizontal beam can support, so there's some weight in the middle of it, right? Some big heavy weight in the middle of it, and it's being supported on both ends, right? So it's being held up just at the ends, and it's able to support an amount. The maximum load is equal to, it's jointly proportional, no, sorry, not equal. The maximum load is jointly proportional to the width of the beam and the square of its depth, while inversely proportional to its length. So what is length, width, and depth? Well, let's take another look at the beam. We could have a beam like this, right? So its depth is how far down it goes. Here is D, the depth. We could also talk about what its width is. Its width is going to be, sorry, that was just me trying to make an arrow pointing at the W, but it wound up looking like a W as well. So width, jointly proportional to the width, and then finally the length of it there. Now, this makes sense. It would make sense that it's going to be inversely proportional, right? The farther out the beam gets, if we've got a beam like this, that's the exact same thickness and depth and everything, and we support it at the two ends, it makes more sense that it's going to be easier to snap it in the middle. The farther and farther we stretch it out on the sides, the easier it is going to be to snap it in the middle. On the other hand, if it's all the same thing, and it's a very short thing, and it's very stout, it's going to be able to support a lot more load if it's supported very, very closely like this. So that makes sense. It also makes sense that if it's wider, there's more stuff there. That if there's wider, it's going to be able to support more, and its depth, it's going to be able to support more. Now, it turns out that it's not just the depth, but the square of the depth. So we have to integrate that into our formula. So let's figure out how can we turn this into just a formula in math. The maximum load is equal to, first thing we have to do, we have to put in that proportionality constant, K. K times, so what is it? Jointly proportional to the width of the beam and the square of its depth, so times the depth squared, because it's the square of the depth, divided by, because it's inversely proportional to the length. So this gives us a formula for figuring out maximum load. We'd have to know what K is to be able to use this formula, but we've got a formula for doing that. All right, now let's continue with the problem and see if we can use that to figure out the rest of these questions. Okay, so now that we've got our max load formula here, if a given beam can support a maximum load of 750 kilograms, how much could it support if its length is tripled, or its width is doubled, or its length is doubled, its width is halved, and its depth is tripled? Uh-oh, wait a second. We don't have any information. Like the way we did all of these previous problems was they gave us enough to figure out K, and then we used K to figure out the rest of these problems. We don't have any specific numbers to work with, so what are we going to do? Well, the first thing we need to do is not freak out, right? We've got this problem, so there's a good chance that we can solve it. So let's just try the things that we normally try with word problems. Let's try to just name things that we aren't sure of at least. We don't have a specific number for the length that it is. A given beam must have a length, it must have a width, and it must have a depth at first, right? We don't know what they are, but we can still give them names. This is a great thing to do, is to just give names to the things that you don't know. So let's say right from the beginning, we'll name that its width, its initial width, Wi, its initial depth, Di, and its initial length, Li. So these all wind up being the initial width, depth, and length, respectively. Now, what do we know when we use the initial width, depth, and length, respectively? We know that 750, the maximum load, is equal to K, we don't know what K is, times Wi times Di squared over Li. Well, wait, we still can't figure out what K is. So what are we going to do? Once again, don't sweat it yet. Let's actually try some of these out. So first one, if its length is tripled. So if its length is tripled, we are going to have a different thing than Li but it's going to be connected to Li, right? If we triple the length of Li, it's going to be 3 Li, so it's going to be 3 times Li. So what is it going to be if we've got K times W times Di, whoops, not W, but Di, Wi, over Li, 3 Li? Well, we don't know what that is, but oh, hey, that looks a lot like this. Oh, that's just a third. We can pull that third out. We've got 1/3 times quantity K times Wi times Di squared over Li. We already know what this is. That's just 750, so it's 1/3 times 750. 1/3 times 750 is 250. What's the unit we're working with? We're working with kilograms as our unit. So the maximum load, if we were to triple the length of this beam, would be 250 kilograms. Great. So now we've got an understanding of how this is working out. We just plug it in and we can use what we've got here. We can use the information that we've got. We don't have to know all the numbers. Knowing just one of them is enough because we've got a general form that it's working in. Width is doubled would be 2 times the initial width, Wi. So that would be K times 2 Wi times Di squared over Li. So we pull that 2 out. We've got 2 times quantity K times Wi times Di squared over Li. We plug in what we know that all is. That's 750. So it's 2 times 750, or 1,500 kilograms would be the maximum. Great. On to the last one. Ooh, this is a lot of things, right? Length is doubled. Length is doubled would mean 2 Li. Width is halved would mean half Wi. And depth tripled would mean 3 Di. Okay, so how does this come out? We've got K times Wi. Our new Wi is 1/2. Sorry, K times W. What are we using? We're using 1/2 Wi times D. What's our new D? It's 3 Di, and this is important. So remember, we're not plugging in for just 3 Di squared. We're plugging in all of this. It's what all the new depth is. And the new depth is 3 Di, so it goes in parentheses. 3 Di squared, so that 3 is going to get squared as well. Divided by 2 Li. So K times 1/2. Let's pull the 1/2 down. And so we'll get Wi up here, but it'll be divided by 4 Li. Times 9 Di squared. So we can pull out the coefficients and we'll get 9/4 K times Wi times Di squared over Li. We know what that guy is. That guy's 750. So 9/4 times 750. Plug that into a calculator and we get 1,687.5 kilograms. And there we are. One thing I'd like to point out is notice that depth by far matters the most because it's depth squared. So you can get a lot more load by just having a larger depth, right? You have to increase width a lot more than increasing depth because depth gets squared. This is why if you've ever worked in roofing or anything where you see a beam supporting a long horizontal length, if you get the chance to look up inside of an attic or inside of a roof, what's actually holding up the structures, you'll notice that the beams aren't flat like this. They're supported like this so that they can have the most depth because it's the depth squared that makes the strength. So they're always supported on a long, deep kind of axis because that gives them the most strength. So if you've done construction, you've actually seen this before. You've seen something where you're like, oh, what you're seeing there is mathematics in effect in the real world. Pretty cool. All right, hope variation makes sense, and we'll get started on the next section in the next lesson. All right, see you at Educator.com later. Bye.